Okay, I'm doing this because we have so many still out, but I want to kind of highlight the difference between what we did before and what we're doing now, because this is a technique that happens when you guys can't separate the variables. You can't use algebraic techniques to separate them. So every problem we've done up to this point, every differential equation we've had, we've been able to split the variables using multiplication division to the different sides. If I look at a problem like this, which just says solve this differential equation, you guys should be able to kind of know exactly what that means to do. Mathematically, if I split the variables to different sides, I get dy is equal to x dx. And when I integrate both sides, I get the integral of dy, which is the integral of x, which is x squared over 2. We still have plus a constant. And I know that my initial condition is 0, which basically means that c is going to be equal to 0. So I plug that in, get c is 0, and I know that this is the actual one. By the way, I need to address over here just a little misconception that was present in many places on the test, which was a little on the quiz. And I'm going to bring this up now, even at the benefit of those who have to take it, because you guys really need to learn this one. What is the integral of 1 over, let's do 1 over e to the x? Negative e to the negative x. It's not the natural log. And I know a lot of you were kind of doing things, so I saw a lot of this happening where if I had the integral of 1 over x squared, people were putting natural log of x squared. The natural log is not a, like, every time you see something in the denominator. There is only one time that that happens, and that is if it's the integral of u du. So if you can ever make that u be equal to something and make it match that form, then it happens. But the integral of 1 over x squared dx is a rewrite. That's x to the negative 2. You integrate that by adding 1 to the power and kind of going that way. The integral of 1 over e to the x is the same as the integral of e to the negative x dx. And the u substitution that you technically do on that one is u is equal to negative x, and du is negative dx. And when you plug everything back in, you get that negative that's pulled out. So this is just the integral of e to the u, which is the integral of e to the u. We'll keep reviewing integration, but that was one that kind of in different forms creeped up. I think a lot of people saw that anytime you have anything in the denominator, it becomes a natural log, and that's not necessarily true. Another thing is that if I have the ln of x plus c, that's not the same as the ln of x plus the ln of c. Those are not the same thing. There is no distributive property of natural logs. If you guys remember the killing puppies mistake of distributing an exponent across addition and subtraction, this is another killing puppies mistake because there's only one operation you can distribute across addition. And what's that operation? There's only one distributive property, only one, multiplication. That's the only one that distributes. No other operation does. That's why if I have the sine of x plus 2, or we'll say x plus 4, that's not the same as the sine of x plus the sine of 4. There is no distributive property of the sign. That does use an operation that if I write down, you're going to freak out for just a second because you're like, wait a minute, do we have to memorize that one? No, you don't. But you remember this? Do you at least remember that at some point you kind of learned that? Sine x cosine 4 plus cosine x sine 4? It was a sum difference property. You guys did it way back in trig, in pre-calc. You don't need to know it. The only two you need to know for trig are sine of 2x is 2 sine x cosine x, and cosine 2x is cosine squared minus sine squared, those two. But, okay, back to this. This is a graph of the solution, shown along with the tangent lines to the curves at integer values on x equals negative 4 to x equals 4. Basically, on my very colored version, you're seeing the instantaneous rates of changes. So I know it looks a little weird, and what I'm going to do is try to, in a visual, like not virtual sense, delete that black line so you guys see just this. So they're the same thing, but this one has the black line, or the black curve, deleted. It's interesting how your brains trace the parabola, and yet every one of those is a straight line. Like, do you actually see the parabola traced in a curvature way? And yet each individual red line is actually just a straight line. What it says is that the graph shows just the red tangent lines from the previous graph. Note that the tangent lines shown provide a roadmap, or we say breadcrumbs, to follow for the solution. Meaning if I put a point here and I had that curve, you guys could actually draw the whole curve out pretty well without having the equation down. So this is the tricky part. This is the part that we're going to spend a little bit of time on. I'm going to pause the video and have the viewer, whoever does it, do this too. On the axis below, we're going to sketch a slope field for the differential equation. And the differential equation, same one from above, dy over dx is equal to x. We're going to sketch that for the 15 points. So here's how this is going to look. I'm actually going to switch to red so I can have this be in a little bit more of a power color. And we'll go no, we'll go hardcore red, red. For instance, let's take this point. That point has an ordered pair of 1, 1. And if I plug 1, 1 into this, I get dy over dx is equal to 1. dy over dx is equal to 1. What's the slope of 1 look like? What angle? What angle is the slope of up 1 over 1, up 1 over 1? 45 degrees. We're going to sketch a little small piece here that's like an angle of 45 degrees. In fact, I'm not going to put the arrows at the end. I'm just going to draw a line through it like that. And on this vertical thing, isn't every single x value exactly the same? They all have an x value of 1. And since the dy over dx is only dependent on x equals 1, we're going to plug in, and they're all going to be 45 degrees. What are the slope, little slope field lines going to look like on this piece here? Horizontal. They're going to be all horizontal. So they're going to look like little tick marks there. And then what are they going to look like here? Yeah. So mirroring the other side, but just a 45-degree angle. There we go. Switch into... Now, every one of these represents an infinite number of possible solutions. I think you guys can realize that you could actually draw even more. You could actually draw an infinite number vertically in every spot and flood this image with this. We're not trying to do that. Every one of those is a possible solution. What makes one different from another? How does one solution, one curve, like if I put a point here and trace what this looks like it's doing, how is that one different from one down here? It's y-intercept. What do we kind of call, not just the y-intercept, but any point? What do we call that single point up here that gives us a starting point? What's that called in a differential equation? You have a differential equation, but then you also have some other point that you can use. That's what I'm looking for, those two words. Initial condition. It doesn't necessarily have to be when x is 0. It just needs to be any ordered pair. So that was one that we actually could solve because we can separate. But here's one that we can't separate. 2x minus 3y. I want you guys to try to take a second and separate that. Zoom. So algebraically, this equation, this differential equation, cannot be separated into dy's and dx's, which means it cannot be integrated. And you're like, thank God, there's something we can't integrate. So what we do is sort of not a cheat, but if you didn't like Riemann sums and you don't like these things where we approximate, this is an approximation. And this is actually what they would used to do with this. You start with an axis on a field, and you're going to sketch a slope field. This one's going to be a little bit more complicated, so this one I actually am going to pause the video and then put up a final response on these. And I'll do one little chain of this, one little piece of this. It's 2x minus 3y at every single ordered pair. It's probably easiest to start on the axes where you have one of them is 0, so then one of them gets knocked out. That's easy. It's also easy to do this one because, and that's where I'm going to start. This is 1, 1. So if 2 times x minus 3y, that would be 2 minus 3, which is negative 1. This is going to be a 45-degree angle like this, just like it is. But then as I move up, this is 1, 2. So it would be 2 minus 6, which is negative 5. How are we going to distinguish negative 5 here? It's going to be steeper. We're going to guesstimate. And then now we're going to do 1, 3. And I'm going to do 2 minus 9. This is negative 8. It should be even steeper than that. So we're moving up and making them steeper and steeper. 1, 0, I'm going to plug in, and that gets me a slope of 2, which is going to be a 45-degree angle, but then actually steeper than that, it's going to be something like this. So we'll just try to draw that steeper than 45 degrees. Sorry, this is not quite nailing where I want it to draw. That's better. And then this is 1, negative 1. So when I plug that in, I get 2 plus 3. I get 5. That should be even steeper than up above. So that's like that. Okay, now I am going to pause it. Beep, resume. If I go along the y-axis where x is 0, then this should be a little bit better. This is 0, 0. And 0, negative 1 is going to be x is 0 minus a negative 1 means I have a slope of 3, so that's kind of steepish. 0, 1 is negative 3, so that's reflecting that, but that's kind of steep down. Then negative 5 should be steeper, and then negative 9 should be steeper there. Then I have negative 1 on all of these, so plugging in negative 1, this should be a slope of negative 2. This should be a slope of, if I plug in negative 1, this is negative 2 plus 3. That's a slope of 1. Then negative 1, negative 1, 1 would be negative 2 minus 3. This is a slope of negative 5. Then this is a slope of negative 8. And this is a slope of negative 11, our steepest one yet. I am not really concerned that you guys can accurately distinguish the difference between a slope of 2 and a slope of 11 on a little tick mark thing. Nor am I concerned that, hey, your slope for negative 11 up there it's less steep than your slope for negative 8 somewhere else. Like, that's not the point. In fact, we use a program, or we have a program. Actually, there's one program that one person wrote years ago that is still like the standard on this. And he actually wrote this, I forget where. I'm trying to see if I can find where slope field is. Differential, dy dx equals. What's the equation? Because I have short memory, 2x minus y. 2x minus 3y. Let's see. Nope. 2x minus 3y. There we go. So like this person wrote this in a way that you can actually kind of see what's happening. And whenever we make our worksheets, we still use this person's program to make them. Because there's like nothing better out now. I think the Inspires can do that with a software update. But you guys would not be able to look from yours to see what this equation should look like. But can you see what the solutions would look like? When you graph a slope field, you actually can start to see what the solutions are going to look like. Why can't you find a general solution to the differential equation above?
Because they're not separable?
Yep, because they're not separable. Okay. So I'm going to return to a good one. We're going to call this one a friend. This one is one that is separable. This is the one that you guys did before. Its general solution was y is equal to x squared over 2. We actually did that earlier, plus a c. Yep?
Can you tell that something is non-separable just based on the graph?
Not based on the graph, but algebraically you'll be able to tell pretty easily. I wouldn't worry about, you're not going to get a problem set that says, is this separable or is this non-separable? You're going to get one saying, it's not separable, now do this. Okay, what I want you to do is put the point 2, negative 1 on this grid. This is a little bit of drafting and sketching, so this is something you guys get to do. Put the point 2, negative 1 down. And take a minute and try to draw from that point the whole solution. You see what I'm asking you to do? You're going to follow the lines where that point is and draw the rest of the curve as best you can. Does it make sense that the further you get away from that point, the less accurate you are? And the closer you are to that point, the more accurate you are? So I'm going to try to sketch this up and just do my best, but I want your sketch to be yours. I don't want it to be mine. I want you guys to follow. Oh, I did, didn't I? Then we'll fix that. 2, -1. Okay. So sketch going up from that point. You guys can draw these as straight curves, or like you can draw them like you're doing little drafting artwork and do little like bits of lines and things. Mr. Consilla showed me that trick of like, hey, if you can't draw, just draw lots of little sketches, and then somehow when your eyes blur, it makes it look good. You're just doing the best you can to try to follow your breadcrumbs. So you or Alice either going down the rabbit hole or through the looking glass, depending on your story. And all of that curve I just drew because of that one point. Does your curve look parabolic? If it does, you did your job. Now, here's the fun part. On the curve you drew, and this is different for me every year, what is the value of y when x is -3? So you're going to go to your curve and try to plot where x is -3 and figure out what is the y value. So I'm going to put a y value of about 1.4. That's where I ended up this year. That's fine. Let's see who is better. So it says compare this to the actual value of y when x is equal to 1.4. So here's the actual value of y. We need to take this equation, y is equal to 1/2 x squared plus c, and plug in my initial condition to figure out what that c value is. -1 is equal to 2 plus c, or c is equal to -3. So you get y is equal to 1/2 x squared minus 3. Now, what's interesting is right away, if you look at your sketch solution, if it doesn't come close to -3 on the y-axis, you're already going to be off. Mine did not go down far enough. I curved it too quickly. I do that every time. So the actual value, if I say what is y when x is equal to -3, the actual value is 9/2 minus 3, or 9/2 minus 6/2. The actual value is 1.5.
Wow, I got so off.
So I thought it was not too bad. I must have curved back up to compensate. Another, like, you can use some tips on this. Like if you know 2 -1's a solution, you know -2 -1's a solution, and go from there. Okay. Now, I want you guys to see what this looks like when it's not separable. So I'm going to take one, like, it's very similar to the one we did before, but it's a little bit of an easier one. dy dx is equal to x plus y. Again, I'm going to swing over to this thing, and we're going to edit this and make this be x plus y as well. Nope, x. Where's my special symbols? Plus y. There we go. There it is on the little program, but obviously I put it on this page for you already. Since this is not a separable equation, we have no direct way of solving it, but it says it's simple for the computer to draw its slope field, and again, that's the best program we found that does it, at least that we can copy paste it onto these worksheets. So given this, and given that it's subject to f of 2 is 1, I want you to put a point down at 2, 1, and draw an approximate solution curve. 2, 1 is right here. I will draw mine. Yours may be better than mine. This is not like I have more math ability, so somehow mine's gonna look better. This is pure sketching, which means I could really be bad at this. So we are following this curve. We're trying to follow what breadcrumbs we see. and my curve is going something like that, and then it swings down, but it's being pulled almost like a vortex, or to be very very current with this, it's being pulled like a black hole. Because for those watching this in the distant future, last week was the first image of a black hole ever. Yeah.
So it's supposed to be like more tangent to the points rather than going through.
Think of it this way. You're only seeing the slope fields based on integer values or kind of other values in between. There's actually an infinite number of those little line marks all over there. So you're just using it to the best of your ability. It could be tangent. At points, it could pass right through. But yeah, it's supposed to be guiding your way along. I think all of you should have, at some reason, that it asymptoted, if that's a word, to this little place there. And it created that asymptote because, well, you get this place where dy dx is equal to x plus y. You can start to figure out what matters there, but there is definitely an asymptote being pulled in. Then it says, consider that given the differential equation subject to that initial condition, draw an approximate solution curve and use your curve to approximate f of negative 2. So let's figure out what f of negative 2 is. So negative 2 is, if I plug in negative 2, I get a point here. And I tiptoe over to where that is on the y-axis, and I'm going to say this is about 1.2. I'm going to put it at 1.2 this year. I think it'd be down a little bit, but yeah. Okay. Then it says verify that y is equal to negative x minus 1 plus 4 e to the negative, or e to the x minus 2 is a particular solution. So now I'm going to say, hey, here's a graph. Is that actually a solution? Okay, if it's a solution, that means that I'm going to do this little proof thing where I put dy dx on one side and x plus y on the other side. And I'm actually going to evaluate and see if this is true. So dy dx means I'm going to take a derivative of this. The derivative of negative x is negative 1. The derivative of negative 1 is 0. The derivative of 4e to the x minus 2 is 4e to the x minus 2 because chain rule is not going to affect that. The derivative of x minus 2 is 1. Constant multiplier, so I have 4e to the x minus 2. Then I'm going to get, I have an x here, plus y is plus negative x minus 1 plus 4e to the x minus 2. And that simplifies to negative 1 plus 4e to the x minus 2. Bingo. They do match. What? First step on, oh, that should be E, yes. And then it says subject to f of 2 is 1. I actually need to verify that that's true, because I could be lying about that. So if I plug in 1 for y and 2 for x, is this a true statement? So plus 4e to the 2 minus 2. So is 1 equal to negative 2 minus 1 plus 4? Yeah, that's true. So my initial condition is okay, and my particular solution to this is okay. Meaning, this is actually a solution at that point. It did it reverse. You guys can't really easily separate these at all and do that, but it gave you what a solution is. So let's read what it says. It says find the exact value of f of negative 2. So it's like, yay, we verified that we have a solution. Now let's figure out what f of negative 2 is. F of negative 2 would be 2 minus 1 plus 4 e to the negative 4, or 1 plus 4 over e to the 4th. I'd be really impressed if you could get a decimal value of that in your heads. And next year in Calc, you actually will learn how to get a decimal value of that in your heads. But not now, and you don't have to do it at the moment. I'm going to plug this in my brain and get an approximation of 1.07326. I'm kidding, I had that written down. So the closer you were to 1.07 up above, the better you are. I was 1.3 last year. I was 1.2 this year. I'm getting better. But my curves still aren't great because I, suck at sketching. Okay, before you get all excited, we're actually going to do a little bit of a part C of this. So if you could pull out the second page, and I'm going to cut the video and start recording a second one so I can keep this split.